In this video, we're going to see how counting methods can be applied to help us solve probability questions. Enjoy. Let's start. Cool. So in the previous version of Class 3, we had a look at all of the counting methods. So we were looking at how to do multiplication addition principle, we looked at permutations, we looked at selections. This class is going to be basically around how do I know when to use what, and we're practicing when to use what, essentially. So the basic choices you have, the basic styles of question you can come across are those as follows in these 3 dot points, which I'll just double check I am in fact screen sharing. Cool. So first things first, if choices can be repeated in a sample space, so let's say we have a sequence of digits that we can reuse over and over again, then just go straight for multiplication principle, because you're doing these things in sequence, and all the other counting methods require the number of choices to decrement every single time. So if they can be repeated, just go straight multiplication principle. If they can't be repeated and the order is important, so the order in which you write the terms in are important, like pin codes, for example, doing a 9 then a 5 is very different to doing a 5 then a 9, then permutations would be an effective method. Or if you really want to, you can still use multiplication principle for that. It can be a bit nicer depending on which you prefer to use. If the choices still can't be repeated, but the order doesn't quite matter, this is usually around like teams of people. A team of Kath and Kim is identical to a team of Kim and Kath. The order you write those terms in doesn't actually matter. That's when you're using combinations or selections. Those mean the same thing. That's the NCR term. We're going to see a few examples and then we'll get into practicing. So, find the number of different 4-digit numbers that can be formed from digits 0 through 9 with like no further restrictions other than that. So under these circumstances, we aren't told that we can only use 1 digit in any given spot. We are allowed to repeat digits. So really we're just going to figure out, we're making 4 choices in sequence. Are there any implied restrictions when it comes to creating a number? The only implied restriction is that we can't start with a 0, right? There is no number that ever starts with 0. So instead of having the full 10 digits available to us in that first spot, we're only going to have 9 digits available to us in that first spot. But everything else from there is fair game. You can have any number 0 through 9 in the 3 remaining positions for our digits. So you're going to have 9 by 10 by 10 by 10, giving you a total of 9,000 possible combinations straight from the multiplication principle. From there, if choices can't be repeated, so in this case, very similar example, but this time we can't, where does it say it? Without repeated numbers. So you can't have the same digit appear in more than one spot on the number. Well, under these circumstances, you would do a permutations approach. But one thing I hadn't quite mentioned at the beginning, which was you always have to address any of the implied restrictions early on. Implied or otherwise, I suppose. Right, so in this case, our restriction is we can't have a 0 in the first position. So that means that we're going to start by making sure there's still only going to be 9 possibilities for that first spot. But after we've addressed that restriction, there are no further issues to worry about, and so you can just go straight for permutation to that point, which is that you have 3 remaining choices to make out of a total of 9 remaining digits to choose from. So 9 by 9 factorial over 9 minus 3 factorial, this is the permutations equation here, and that's going to give you that. So that's a permutations approach for it. If you would rather go through and do your multiplication principle idea, that's also possible here. It just means that you would say, okay, I've got 9 possibilities for that first digit, but when I now look at the second digit, instead of having 10 again, because I already used 1 in that first spot, I now have 9 for the next digit. Then, because I used 1 in the second digit, I'll now have 8. Then I used 1, I now have 7. So you could just do 9 by 9 by 8 by 7, if that's a bit more appealing to you. Permutations and multiplication principle are very closely tied. It's only when you start looking at selections, or combinations, same thing, where the multiplication principle is still nice to know, and it does help with certain circumstances like this one here, but the primary way that you solve it is going to be through selections. And as I mentioned at the beginning, it'll be sort of like when you're dealing with teams of people. So in this case, we have a team of 3 boys, team of 3 girls, and they're to be chosen from a larger group of 8 boys and 5 girls. And we want to figure out how many possible teams there are. Again, this is teams. The order in which you write these names in won't matter, so we're going to use selections. Now, teams comes up fairly often. The way you would be best off thinking about this is making your selections in order. So selecting boys first, then girls, or girls first, then boys, doesn't really matter. Just the fact that you're making them in order would be a good way of thinking about this. So if we say the first choice is to create the boys team, you would say, I have 8 boys and I'm choosing 3 for the team. So there's 8 that I could choose from, and I'm choosing 3. That's going to be using your selections equation, 8 choose 3. That's what that looks like. That's going to give you 56 total groups. Then next would be choosing 3 girls from a total of 5. So again, same idea. Order doesn't matter in which you write them in, and so you would use your combinations for that. The selections equation, that's going to give you 10 unique groups. But because this can be arranged in any order, right? You could choose boys then girls, or girls then boys. It's a multiplication principle. You're doing it in some sequence. And so you just take the number that you got from the boys, multiply by the number you got from the girls. That's going to give you the total number of combinations. So in all cases, when it comes to solving probabilities around that, because we kind of didn't really solve probabilities, more so just found the combinations. What we've just discussed is essentially step 1 of how you would go about, well, I guess it was step 1 and 2, really, where what you want to do is you want to figure out the total number of combinations in your given scenario. And again, you can do that using the decision framework I mentioned earlier, which is repeated choices is multiplication principle, non-repeated but order matters would be permutations, and then the last would be selections. Then from there, it's pretty unlikely that you'll be able to use this idea again to find the number of combinations that meet whatever the probability is. And that's because, if we see this example here, right, there was an implied restriction, which was that the first digit couldn't be a 0. So you usually can't use permutation selections right out of the box. Sometimes there's got to be some additional things you have to concern yourself with first before you can then put it in at the end. That's where this gets a bit more challenging. It's usually a lot easier to find just total number of combinations, broadly speaking. Once you have total number of combinations and the ones that meet your probability, well, at that point you're just dividing them by each other to get your final probability there. Is there anything I need to clarify before we dive into some practice questions together? If so, let me know. Otherwise, we shall make a start on 10D, which, yeah, I'll do a screen grab of this. This will be good to refer to. Okay, we're just going to go top to bottom. If we get too many repetitions, I'll skip some, and we will see how we go. That should be, has to be that zoom level. All right, we'll start from the top. 4-digit number from numbers 1 through 6. No repetitions are allowed. Find the probability of an even number. So I'll let you have a think about what's going on there. Yeah, have a think, let me know. Some of them you'll find you don't have to like be super strict with. Like this one does have a pretty easy shortcut. So I'm curious if someone will find it. Probability even, 3 out of 6 equals a half. Yeah, so a half is good. I'm curious to hear where you got the 3 out of 6 from. Let's see. Where could that have come from? Is it just from your sample space here? You had 3 numbers that were even out of 6 total? Yeah, so that's the shortcut there. This was a pretty basic one. You got 3 possibilities out of a total 6. And so you can just go straight for the throat there and say you got 3 out of 6 for even. And so if you're also looking for odd, well, sure enough, that's also going to be a 3 out of 6 or a 1 out of 2. Just for the sake of following a more bulletproof procedure, here's how you would do it if it was a bit tougher. You'd have to follow a sort of decision framework, which is we have no repetitions allowed, and the order does matter. So this would be a permutations type of equation. So if I said find the number of possible digits you could make, you would be using permutations here. You would get a total of 360. From there, you would want to find the number of even combinations. And so you'd be like, okay, any even number that we could make out of this would have to end in either 2, 4, or 6. So you've got 3 choices for that last digit, because that's how your even numbers have to end up. Then, from anything else, you've just got 5 choices remaining across the remaining 3 digits at the front. So you're going to have your 3 choices, which are for that last digit, and you can do the permutations to get the remaining selections, or you can just do your multiplication principle there and say, I've got 5 for the next, 4 for the next, and then 3 for the last. And then all is said and done, long-winded way of getting to a half. So, as I said, more effective for more complicated questions. But that's how you would get it if you needed combinations. Odd, same thing. All right, that's that one. This one also has a similar shortcut, part 2. So, let's see how you go with that. Or question 2, rather. If you're running into troubles, let me know. Either by like a hand raise or a, yeah. Not too sure. Okay. So for this one, if it is something you're not too sure about, then my recommendation would be to follow the procedure I outlined, which is first decide Well, can choices be repeated in this case? That'll be the first decision to make when figuring out number of combinations. Can we make repeated, can we choose the same letter more than once? What do we think? Yes or no? If you imagine the letters of the word computer in a bag and you had to arrange them in certain ways, could you use the letters more than once? Okay. For this one, it's supposed to be implied that you're not allowed to use multiple of the same letter. So like, for example, I couldn't use 3 C's. I've only got one. Imagine like Scrabble, right? You can't use more than the letters that you have in the bag. And so because we can't use any given letter more than one time, that's what's supposed to be implied here. But fair enough. You'll see that once and now you'll know. So this is an example where you cannot use the same letter more than once, so choices cannot be repeated. So we can scratch that one off. Next up is you want to find the total number of possible combinations with that in mind. So that'll give you your denominator for your overall probability. So when we think about the number of total possible combinations, we could arrange these. You've got a total of 1, 2, 3, 4, 5, 6, 7, 8 total letters, and you're trying to arrange them into 3-letter words. So basically the question becomes, how many different combinations are there where I can arrange 8 letters into 3-letter words? Anyone know either what the answer would be or how to calculate it? We started off by 8 over 7 take 3 with the factorials. Yeah, because you have 8 total, so n is going to be 8 and r is going to be 3. So yes, you'd have 8 factorial over 7, or hang on, it wouldn't be over 7 take 3, it'd be 8 take 3, because the equation for permutations would be like this. I'm trying not to show too much. So it's n factorial over n minus r factorial. So you're going to keep the same 8, but otherwise, yeah, subtract 3. That will be the factorials approach there. Otherwise, you could just say, I have 8 choices for the first position, then 7 for the second, 3 for the third, and then that would be your total combination, 8 by 7 by 6. So that's that one. That gives you total number of combinations. The next thing you want to do is figure out how many of those combinations start with a vowel. So again, same idea. If you remember from last time we did this, it was you want to focus on the restriction first. So what does it mean for how many selections do I have given that it has to start with a vowel if I'm picking my first letter? How many vowels do I have access to? Three vowels in total. If we choose one, we'll have 2 left. Yeah, correct. So what you have is, when we're looking for probability of starting with a vowel, start by looking at that restriction, which, as we've just said, we have 3 possible choices for that first digit, right? So 3 possible vowels, one of them is going towards that first digit. Then from there, there's no further restriction. The word starts with a vowel, the rest can be whatever they want to be. So we've chosen one of the 3 to start with, so you're going to start with a 3. Then you've now got to consider how many letters in total do I have left for my next choice, and then the next one until you fill out the word. And so what that ends up looking like is you've got 3 for that first position, so that will be like this one here, 3 for the first position, and then there used to be 8, but now there's 7 because you've chosen 1 letter from that bag. And then, of course, from there you just keep decrementing on and on and on, which would mean permutations, or you can just do this. Which it sounds like this is a bit more what you guys are looking at doing. So, yeah, it would just be that. That gives you a total number of combinations that meet your probability, and then you divide that by your total number of combinations. So this is a process I use if I'm ever confused as to what I'm doing. You just go brute force it, number of combinations available, and then do your division. Now I did mention at the start this one does have a bit of a shortcut, and that is simply that we have 8 letters. The word starting with a vowel, there are 3 possibilities, and so when you think about choosing your vowel, you've got a 3 out of 8 chance of picking a vowel when you pick that first letter, which is why it simplifies down to 3 over 8. So kind of like how this one had a shortcut, which was just a half, because half of all numbers are even. This is also a shortcut that you could use. But the shortcuts in this I've found are few and far between, so it's good to be able to practice this no matter what. Is there anything I need to clarify about how we handled that? Let me know. Otherwise, have a read of question 3 and we'll see how we go. And yeah, if as a reminder, like these are the kinds of questions where it's a very steep learning curve. So don't be at all shocked if you get like 90% of these wrong when you're starting out. Once you see them for the first time, or even the first few times, you'll start to see the patterns. So getting used to these early on is a pretty good idea. But yeah, again, just sing out if you want me to have a look at question 3, or maybe even let me know you're working on it. Yep. Nice work, Sanjay. Not too sure? Okay. Cool. So, unless Pia has something she wants to start us off with, I'll have a look at this. Okay, so letter H is first. This one does have a shortcut to apply here. That being that because it's kind of the same thing here, right? Word starts with a vowel, word starts with a H. So if you think about shortcuts, again, it's going to be, I have this number of letters, I have 5 number of letters, and one of them is a H, so the probability I select a H on my first go is going to be a 1 out of 5 chance for that. And so that would be the shortcut to immediately solve that. However, again, we're looking at what happens if we don't see that shortcut. And so again, we're going to look and say, okay, do I have the possibility of repetitions? Well, again, this is that sort of Scrabble situation. You can't have more than one, you can't use more than one of the same tile letter, and so no repetitions are allowed. We also know the order is important here, so the way that you arrange these words is a unique combination. So we start by figuring out total number of possible combinations in the scenario, which is a permutations, because the order matters and there's no repetitions. Or again, you could say 5 by 4 by 3. Right, you could do that as well. Either way, you'll get 60 total combinations there. From there, letter H being first, well, if you look and think in terms of positions available, you've got 3 positions to put your letters. The first one has to be a H if we're now looking for number of combinations with H first. And so you only ever have one choice for that first letter. Then, from then on, because you've chosen one, you've now only got 4 remaining. You've got the EAR that are left over, so 4, and then again, you've chosen one more, down to 3. That's going to be a total of 12 remaining choices that you have. That, or just use permutations if you like that at all. Then you just do number of combinations we want divided by total number of possible combinations, and that'll eventually get you back down to the 1 over 5 that we found via shortcut from before. If I need to clarify that any further, let me know. Otherwise, see how you go with part B. In fact, I'll even leave this up here because you can see the question and you can at least see a kind of approach that you can use to go about it. So that should be helpful. Even if it is a slightly different approach, you can see the logic, or a similar logic. Oh wait, this one is nasty. I'll be surprised if anyone gets this one, but yeah, okay, this will be a... I'll let you guys have a shot. There's a possibility you find it. I'll be surprised. So I guess I'll just say don't spend too long on it. Sing out early if you're completely lost. But once you see it, you'll see it. Isn't it 1 out of 5? For part B, is it 1 out of 5? Not quite. The letter H being chosen, the key difference here is that it can now be in any position. So 1 out of 5 was to get it in the first position. However, it could also be in the other 2 positions. So that also matters. So not quite 1 out of 5. I mean, I'm kind of just assuming that's what you thought. I wasn't too sure your rationale behind why 1 out of 5, but those would be what I would be considering. The fact that it can be in any one of the 3 positions is important. Welcome, Apraj. We're just working on this question 3b. 1 out of 3. Not a 1 out of 3 in this one. Yeah, I'll jump in on this one. So I think I like where your idea was there. 1 out of 3, was that because you got 3 possible spots to put the H, and so it was a 1 out of 3? I like the idea at the very least. You were considering that there were multiple places to put it. However, here is how we handle it. So the good news is A, B, C, whatever. When you're looking at a combinations approach to solving this, the total number of combinations will apply to all of these scenarios. What we have to do is figure out how many combinations have a H in them somewhere. Now the good news is we actually already figured out how many have a H in the first position. We figured out that there were 12. From there, there's 2 other spots it could go, either in the second position or in the third position. So in the second position or the third position, oddly enough, it ends up being the same thing. Because when you look at this sequence of multiplications, you're either going to put the 1 at the front, in the middle, or at the back. And so wherever you put it, the remaining spots will still be 4 and 3. Because you take 1 from your total of 5 letters, that'll bring you down to 4, and then 1 further brings you down to 3. So essentially what you have is this repeated 3 times in total. And so you have 12 combinations where H is first, 12 where it's second, 12 where it's third. Add them all up and then divide. Or again, if you're using the shortcut, if you already know it's 1 out of 5 for H being first, then you just repeat that 3 times for a 3 out of 5 chance. Clear enough what was going on there? Let me know otherwise. Although it would seem I had a alternative approach, which was you can use complement probabilities. But I'll just pause for like 5 seconds if anyone wants me to re-explain this. Okay, so the alternative idea using complement probabilities is to say, okay, well, it's a bit of a pain, hypothetically, to figure out the number of possible spots that a H could be. So instead of figuring out where can a H be, I'll figure out where a H is not present at all, and then subtract that from the total. Because if I get rid of all the spots where there is no H, then I'm left with only possibilities where there is a H. And so that ends up being, okay, I can't put a H anywhere, which means instead of having 5 total letters to work with, I now only have 4 total letters to work with. I have 4 total to work with. I'm choosing 3. Permutations gets you to 24 possibilities. Subtract that from the 60 total, giving you 36 outcomes that have a H in them somewhere. So that's another way of doing it there, using a complement probability approach, if this wasn't to your liking. If I need to explain that in any more detail, let me know. Otherwise, it'll be part C, which we move on to, which would be both vowels chosen. While you guys are working on that, by the way, Upraj, if you want to check the chat, you'll see a screenshot for a problem-solving framework for solving these kinds of questions. That should help if you have a scenario where it's a bit tough to see what's going on. You might use that framework to help out. Because even though there are some shortcuts, they don't necessarily always exist.
Chris, could you resend that one in the chat because since I joined late, it's not on the chat for me.
Oh, really? I thought it's a persistent chat. If you scroll up, nothing happens.
Yeah.
Bugger. Alright. I'll grab that again then. That's this. Yeah, really? Okay. Can anyone else not see anything past what they've scrolled? Because I can see everything back to like back to when we started this whole thing. That's interesting. Anyway, we're doing 3C from here. Yeah, it's also worth noting this one does use a technique you've already used for solving, so this one I would say spend a bit of time on if you can try to figure this one out. Not as unique as the previous one. But if not, happy to jump in. Has anyone made any significant progress? Any thoughts initially when it comes to how you might approach this? Would anyone prefer if I just worked top to bottom on these and just sort of ask questions along the way how he might go about it? Would you prefer if it was like me dominant going through it all? Yeah, okay. Cool. We'll do that instead. Cool. So both vowels being chosen. So kind of like how you're looking at the letter H being chosen, it's a very similar idea where the H could be in any particular order. Right? It could be in the first position, could be in the second position, could be in the third. Same idea here, but now we're dealing with two things, right? So now we've got two vowels that are going to be guaranteed in our spots. So they could either be in the first and second position, they could be in the first and third position, or they could be in the second and third position. I hope I didn't double up on any of those. Point being, there's three possible places you could put those two vowels in. So one way of thinking about that would just be to do, okay, I've got, those number of positions that I could put my vowels in. Essentially, the way that simplifies down to is both vowels being chosen means the vowels can be in any order. You've got two factorial ways of arranging those vowels. From there, you've only got one final position to put your to put a final letter in there. You had 5, you've now placed 2, you've got 3 left. And so, since you have 2 choices for the vowel order, 3 choices for the final spot, you've got a total of 6 possibilities. And because the constant can be in any one of 3 positions, so this is again handling the fact that the vowels and consonants can be split in any which way, you're gonna, because again in sequence you've this was us choosing our vowel position. This was us choosing our consonant position. So because you've now got a final 3 possibilities, you multiply by 3, because again, it's going to be multiplication principle there. That's a pretty high level way of thinking about that. If you just want to bash out combinations, that works fine as well. So it would be like, we could look at the scenario where there's vowel in position 1 and 2. So it would be 2, 1, and then 3, because you've chosen, so that's 2 possibilities for vowel, 1 possibility for vowel, and then 3 for consonant. Then you got the possibility, which is, what would it be? So you could do vowels in position 1 and 3. So 2 possibilities there, 1 possibility there, 3 here, and then 2 and 3 will be the last combination. So 2 vowel, 1 vowel, and then 3 consonant, which again, 6, 6, 6, adds up to 18 possible combinations. So you could bash it out that way if that's a bit more visually appealing. From there, you just divide by your total number of possible combinations from the very beginning, giving you a 3 out of 10 chance for that. Any further explanation for that, let me know. Otherwise, the next one will be question 4. So I'll pause like 5-10 seconds. Someone let me know if they want me to re-explain that. Okay, so next one up. 3 men, 3 women, randomly seated in a row. Find the probability that both the end places will be filled by women. So first thing you want to consider is, can we have repeated selections? So can we put the same person in multiple spots? Hoping that's an easy question to answer. Can you seat one person in more than one seat? Yes or no? I think everyone's a bit concerned based on the past few questions. Yeah, so basically 3 men, 3 women, we can't sit the same person in more than one spot, right? If I put Tom in one spot, I can't clone him and put him somewhere else. He's going to have that spot. So choices cannot be repeated, basically. Tom sits where Tom sits, and that's it. So what that implies is either permutations or selections. And that will depend on where we go next. Every time we solve a question like this, we want to start by finding the total number of possible combinations. So if we ignore any restriction, how many ways could we arrange 3 men, 3 women in a row? If we don't care where the men or women go, we just want to see how many ways can I arrange essentially 6 people in 6 spots. Any thoughts on how we handle that? We'll just go in order. So we have 6 available positions for them. At the very beginning, if we had 6 people to pick from to put in position 1, then we have 6 choices for position 1. From there, we've chosen one of the people. We have 5 remaining people for that second spot, then 4 for the next, so on and so forth. This is just 6 factorial. And so 6 factorial, I've already got it pre-solved elsewhere, which was 720. So our total number of combinations, NT, is going to be 720. So that tells us our denominator for our probability. Now we got to figure out the probability that both end places will be filled by women. So, as I said, when you're dealing with a restriction, the idea is to handle that first and then backfill all the remaining spots from there. So, we got to figure out in the beginning how many ways can I fill 2 end seats with 3 women, essentially. Because you want to fill those end places with women. This whole thing simplifies down to, or at least the beginning of it simplifies down to, I have 3 women, 2 places to put them. How many combinations would that be? Or better, how would you find that? One, two, three, 4, 5, 6. I've got 3 women. I want to put one of them in this spot. That's 3 choices. I've made a choice. One of the women is there. I've now only got 2 remaining choices for this last seat. That's all. So 3 people to put in those 2 spots. That's going to be how you arrange that. From there, the rest of it doesn't matter. You've now made you found the number of combinations with that restriction in mind. Now we just go back to the fact that anyone can be anywhere, which is we've chosen 2 out of a total of 6, which means we have 4 remaining people to arrange. So you could put a 4 here, 3, 2, 1. And so this is just going to be 3 by 4 by 3 by 2 by 1 by 2, which when you multiply that all together is going to give you 144. And so that's going to be your nx, the number of combinations which have the restriction in mind. Then from there, at this point, I'll show the pre-written version, which is, well, you do your 144 divided by your 720 there. That's what's going on, which ends up being a 1 out of 5 chance. Now, is there a shortcut there? Find the probability both end places will be filled by women. 2 out of a total 6. Nah, I'm not seeing any shortcuts there. That will be that. Let me know if you want me to explain that in any more detail. I'll pause 5 seconds or so. Otherwise, next up, question 5. Okay. Netball team, 7 players, is to be chosen from 6 men and 7 women. Find the probability that the selected team contains more men than women. So again, first decision we need to make, if we look at the problem-solving framework, can choices be repeated? So can I choose the same person to fill multiple spots on the same team? Yes or no? The question was, can I choose, what was the question? Right, so the first decision we have to make is, can choices be repeated? That will determine the kind of approach we might use. So we have a netball team, 7 players to be chosen from 6 men, 7 women. Can I choose one person to fill more than one spot on the team? No, easy, yeah. Same thing with the seats example. So that means when we're looking for our restriction, we're going to be using either permutations or selections. The follow-up question would be, because we're doing teams of players, do we care about the order in which the players' names are mentioned? Yes or no? Like, is a team of Jill and Jack any different to a team of Jack and Jill? No, correct. So when we're going for our, when we're doing our restriction, a selections approach would be appropriate for this, at least when we're doing our restriction. So that'll help out for the next bit. But for now, when we're doing our probability, because we are finding a probability, we need to find total number of possible combinations. So we have 6 men, 7 women, creating a team of 7 players. Assuming we don't care how many men or how many women are on the team, we just want to look at total number of possible combinations. We've already said selections will be appropriate for teams. So how might we apply our selections equation? Remind that we need an n value. So if I start writing it out, we would have n factorial on n minus x factorial, x factorial. I think I said it before, it was r. Point being, n is going to be your total number of people that you're selecting from, and x is the number of people that you want to pick. So based on, well, n equals 6, yeah, actually, it ends up being the other way around. So n is the total number of people you're pulling from. And so if we don't care about any restrictions necessarily, we have, if we don't care if it's like men or women filling the team, you actually add these two together now, because we're not really discriminating based on gender there. So you end up having 13 total people that you're pulling from, and you're selecting 7. And so it ends up being 13 factorial. I'm hoping yeah, it does focus on. Nice. 13 factorial, 13 minus 7 factorial, because we're choosing 7. 7 factorial, which you should practice expanding these out, knowing how to simplify these. Does anyone want me to expand that out? Or are we happy enough with how factorials simplify? Just a quick yes or no for expand or not. All good? Okay. So final answer for that would be 1716. 1716. That'll be the total number of combinations that we care about. Now from there, we now have to have a look and say, okay, find the probability that the selected team contains more men than women. So again, a selections approach will be appropriate here. But the thing is, there's multiple combinations which would, well, there's multiple scenarios, discrete scenarios, where there will be more men than women on the team. 7 total people. If you think about the fact, sorry, say that again. If you think about all the ways, or all the possible proportions of men to women, you could have either 4 men, 3 women, you could have 5 men, 2 women, or you could have 6 men, 1 woman. So all of those individual discrete scenarios have a team which has more men than women on them. And so my recommendation there is you do those individually, like those discrete combinations, and then because they are mutually exclusive, you can't have those combinations. You can't have 6 men, 1 woman, and 5 men, 2 women at the same time, because they're mutually exclusive. They add together. And so we have our final set of combinations here, the total. When you're doing split groups like this, you can think of this like doing choices in sequence. I think we saw a previous example similar to this, which was if you're choosing 6 men, 1 woman, of the 6 men, you're choosing 6. So you would do the 6 choose 6 using the selections equation. And then because you're also choosing 1 woman, you would follow that up with a multiplication of 7 women choosing 1. So that's 7 choose 1 there for 7. And then you can see the remaining sets of combinations. Well, you're just decrementing the x on one side and incrementing the x on the other. and you can see how that plays out. These would be CAS, by the way, so don't feel like you have to write all of this out. These would be CAS. And then yeah, right, add them all up and divide by the total, which when fully simplified would give you this. So yeah, sometimes you'll have, it's kind of like for those who were there for it, the commute example, where we were looking at like ways you could go from, was it Adelaide to Perth? I don't remember. It was some trip and you could take mutually exclusive choices, which was you could do bus, you could do plane, you could do plane then bus. Since those are all mutually exclusive, the addition principle applies. So you'll find a combination of these things is often required for more complicated questions. Okay, that's that. Yeah, this one was nasty. Yeah, I'll just go through this one just to finish it up. Haven't got much time. So this one, again, is a sort of unique scenario. A lot of this is going to feel unique to begin with. We have a sandwich. We can choose any combination of ingredients, find the probability of the sandwich, whatever. In any case, probability, you always want to find total number of combinations first. This one here, you're going to solve using sample spaces. So basically, to find the total number of possible combinations between lettuce, tomato, carrot, cheese, all that, this one's unique in the sense that you have a situation where if you imagine like going to a Subway and you have your possible ingredients laid before you, you have the possibility of selecting lettuce or no lettuce, tomato or no tomato, carrot or no carrot. And so really it ends up being that you have two choices at each stage on here. So 2 times 2 times 2 times 2 times 2, 2, 2, 2. Ends up being 2 to the power of 8. But with a slight nuance there, which is that you can't have nothing on the sandwich, which they didn't really say that. I don't know if 2 loaves of bread really just count as a sandwich. Probably does, but the book disagreed and they said no, you have to have at least one combination, at least one condiment on there. Condiment, filling, have something in your sandwich, which is why you're going to have 2 to the 8 minus 1. And then from there it will just be very similar vibes to what we were talking about before, which was, does it contain ham? Well, you could do all the combinations that contain ham and do that in an order, or you could use complement probabilities and then just say, because ham is guaranteed, sorry, I'll say that again. What I'm proposing here is because ham is guaranteed, when you go in your order of 2, 2, 2, 2, 2, when you hit the ham, you're forced to include it. So you've only got one choice there. So instead of 2 to the 8, you've now got 2 to the 7. That would be how you go about that. Okay, we've hit time on that. All these are fully worked. Like, I've done this for every single counting methods chapter. So I know this is tough. I would say have a read of them, the 10D specifically and the chapter 10 review. Just go through them all, see the similarities in between. There's not, like, I know it feels like a lot of this was new-ish. I think we've covered pretty much every unique-ish scenario as far as how you approach things. It's always going to feel unique in the sense that you've got different style question, but at a certain point you do crest over that learning curve and things become significantly easier. So chapter 10D and chapter 10 review, those are all solutions in the school classroom. You'll see those in their respective spots as far as like where the counting method stuff is located in probability. And yeah, I guess just give those a shot. This will be the last time we cover it in class specifically. So if anyone wants me to go through it on another class, just send like a, oh shit, I forgot to check questions for this one. Hope no one submitted a question for this, but I'll check that afterwards. Anyway, I'll hang around for a little bit. Otherwise, take care.